a week from Wednesday. You got a plan already. I'll tell you what. So I suggest we start class early and start the exam so I can give you a full hour, right? That is my suggestion, right? But I have to have everybody agree to it. So if you don't agree to it, you don't like this, so we'll just run it from 8 to 8:50. And I'm not gonna out you in front of your friends. So if you've got some kind of problem with it, you can just email me privately and let me know. If everybody in the class agrees to it, we'll start at 7:50. I'll give you an hour. Unfortunately, we've got another class coming in right after, so that's why I have to go a little bit early. And let's see. So what the rule will be is I will, so here's the way the exam is going to be. It's going to be just like, I know it's going to be like one of your quizzes or assignments. I'm going to have an assignment up on Blackboard and you can look at the exam on there. In the classroom, I'll put it up on the screen too, so you can see it. So bring paper and pencil, write your answers down and take a picture and upload it. It's like you would with the assignment. And I will give you I'll give you a grace period, like till 9:05 to have it. Everybody okay on that? Now, I'm gonna make the wild prediction. I bet you guys would appreciate a review session. Am I correct about this assumption? Okay, so how about this? I think review sessions tonight are a bad idea, so. Anybody got a problem with 6 p.m. Monday night? Anybody got lab or some kind of other disaster like that? But
I get out of practice at 6. I can still make it up.
out of practice at 6, you'll be good to go. Nobody's ever let me go in 15 minutes. So. Anybody else got?
I have a lab and like.
That's probably not going to be an issue. You're still well under the record.
Same.
So you guys are okay? I could roll it up to 6:30. One second.
Yeah.
6:30 is better for you?
Yeah.
What do I care? How about that? Okay. Step 2, I've got to get a room. So don't hold your breath on this, but I'll let you know next time. Actually, I'm sure that'll work out. You know how late you guys to get into the buildings? I think it's like 8 or 9 o'clock at night, right? Yeah. So last semester we had somebody didn't show up till like 8 o'clock. First of all, that's risky. Second of all, he was like throwing rocks at the window. I thought he was in love. So make sure that you get there just before the building closes. Okay. Okay. Questions? Yes.
For the review session.
Oh, yeah, that, again, we'll see how the technology works for it, but I'm planning on that, yes. Others? Yeah, I recommend that you be there if you can, but also, you know, I plan to put it on Zoom if the technology works out for me, and also I plan to record if the technology works, so if you really can't make it and be on Zoom, you can always email me a question, and I'll probably look at that before it starts. Okay, questions? Okay, so what we're going to do is we've got basically 3 more sections. I mean, if you look at the syllabus, I've got listed section 2.5, 2.8, 2.9, and that's going to be it for chapter 2. Monday's a recap day, and then we'll have a review later, obviously. But so what I'm going to do in section 2.5 is a little bit different. It's the theme of 2.8 and 2.9 will be a little bit different, although under the same umbrella. So oftentimes you get what's called matrix decompositions or matrix factorizations. So what we know how to do so far is you all know how to multiply. If I have an n by n matrix and an n by k matrix, you can multiply that, right? This is sort of in reverse. If I have a matrix, can I break it apart into a factorization? Well, the first question is why the heck do you want to do that? And the reason for that, the reason for it is sometimes if you can factor this into sort of easier matrices, it makes computations a lot easier. It makes computer algorithms behave more efficiently. You have to do less arithmetic operations and so forth. There are a number of ways that matrices can be decomposed, and we're going to see some later in the course as well. So this is kind of a warm-up first look. This little section here, 2.5, about factoring matrices is very kind of computational. I'm going to talk a little bit about why you would care and a little bit about what the theory is, and I'm going to show you how to do it. It's very kind of algorithmic. And then I might actually bleed into 8 today as well, but we'll see how things go. So if I have an n by n matrix, right? Then what is an element factorization of A is factorization of the form A equal to LU. No surprise there, but yes. Yeah. Up there, yeah. Okay. So, I'm going to factor this into the matrix. Now remember, this got to keep in mind that A was an M by N matrix. And so if I break this down, it's got to be something compatible. Now, what's special about this? L is L for lower triangular. And this lower triangular is often what they call lower triangular unit matrix. It is n by m. So it's actually square with ones on diagonal. So I'm going to factor A, and the first piece is going to be a square. It's going to match the M, so it's n by m, and it's going to have the form this lower triangle, and I've got ones down the diagonal. That's what it's going to do. And U is an echelon form of matrix. This is not necessarily a row reduced echelon form. It's just an echelon. So it'll have pivot columns and all that, but the pivot columns, the entry doesn't have to be one, and it doesn't have to be row reduced. Right. So why would we ever want to do this? Why would we care? So here's one motivation of many. This is often used computation for solving a system of matrix equations. So if I have a system of these matrix equations here, A is an n by n matrix, this is an Rn and this is an Rm, and I have several of them. That several could be just one, or it could be a whole list. Then this is often computationally efficient to do it in this. So so I'm going to show you the process that you might use to solve just like a single one of these. So for example, if you're trying to solve A, X equals B. Now, let me ask you a quick question before I kind of go into this. Let's look at what the L part of the LU factorization, assuming I can get it, looks like. It's a square matrix. So L should look something like this. This could be anything. This could be any other things. So this has to be square. Let me point this out. Square, lower triangular, and ones on the diagonal. By the way, given what we've studied lately about matrices, can anybody identify some super sexy property of this particular matrix we've been looking at lately?
Then invertible,
It is invertible. How do you know?
because it's BL4
Well, no, it's more, it can be much more than 4x4. Yes. That is right. It's got a pivot in every column, right? And so, I don't care what these little stars are down here. If I work up, so I can take this one to take all these out. And once I've done that, I just want to take all these out. I don't care what they are. This has got a pivot in every column, so it's invertible, right? That's kind of a nice observation because if I have an LU factorization, then let's just assume that I've got one. Then I know that this is invertible. And I also know from my previous class that I can solve this partially this way. And now to dig X out, all I've got to do is solve this. So take L inverse and do its magic to B, and this will be some new vector. And now I've got to solve UX equals this. And what's the good thing about UX? Well, U is in an echelon form. And so ostensibly I can back substitute to do this. Yes, sir.
Are all the stars in L, are they all the same number?
That's a good question. No,
Okay.
no, not necessarily. I put the stars, but they can be a generic anything. Yeah. Okay, so once I get down to here, if U is in some kind of nice echelon form, then I should be able to kind of pick up the solutions fairly easy. So let me give you an example. Let A be the following matrix here. 4, 1, 4, 2, minus 4, minus 4, minus 2, 2, 8, 2, 9, 4, and 12, 0, 16, 8. Okay, so suppose I've got this matrix here. This matrix actually has an LU factorization, and I'll tell you what it is. Now, you may wonder where I got this. Did I just pull this out of the hat? Don't worry about that yet. I'm going to show you how you can get this, and we will actually come full circle and figure out how to get this. But for right now, let me just tell you what this is. That is minus 1, 1, 2, 1, 3, 1. And the U piece of this is 4, 1, 4, 2. That's the same first row. 0 minus 3, 2, 4. 0, 0, 1, 0, and 0, 0, 0 minus. And yeah, and so if you wanted to check me on this, you can verify that if you multiply this L times this U, get back to your original point. Right? Now, again, it's probably not clear how I decompose this, and I'm going to show you how to do that. But for right now, if you just multiply this out, you can check and see that this, yes, this is an LU factorization, because this is a lower triangular matrix, one's on the diagonal, and this is an echelon form, right? It's not reduced. These three of these pivot entries are not one, and I haven't reduced the other stuff in the column, but that's an echelon. Now, suppose that I had, suppose I'm trying to solve AX equal B, and B I'll have 3, 1, 1. So I am actually going to go through this. The first thing that I can do is, along the lines of doing this, we're going to solve this equation sort of in tandem. That's what we're trying to solve here. I can rewrite this as I observed before. Now I've got an LU factorization. And so I'm going to solve actually two equations. So and with y equals ux. So notice that these, notice what I've done is I've taken this equation here, ax b, and I've broken it up into constituent parts. I have ly equals b, right? And yeah, and y equals ux. Because I'll put this y back in for ux, I get lux b. So what I'm going to do is I'm going to find the solution y first. So let's do an augmented matrix here. And actually finding this y, because of the form of L, it's not difficult. Let's see what L is. It's 1, 0, 0, 0, and minus 1, 1, 0, 0, 2, 0, 1, 0, and 3, 1, 1, 0. And the y, I guess, I'm sorry, look. So my bad. That should be a B there. The V here is this. Well, okay with that? Simple. And actually, I'm going to do a step of row reduction, and then I'm just going to back substitute, because the row reduction step is pretty quick. So the row reduction is going to be. Let's see, I can just add this to this, and that's going to be 0, 1, 0, 0, and I'm going to 4. Right? And -2 times this plus this, I'm going to get 0, 0, 1, 0. That will be real convenient. -2 times this plus this is going to be -5. And finally, -3 down here. And let's see, -3 times this is -9, and 2 is -7. Everybody okay so far? And actually, because it's so easy at this point, I think I'm just going to kind of pull the solution off, right? Because what we get here is, let's say y1 is equal to 3, y2 is equal to 4, y3 is -5, and I have one more equation satisfied here. And this last one says that y2 plus 2y3 plus y4 is equal to -7. And I know what y2 and y3 are, so that should help me out. It should be 4. 2 times y3 is -10. So this is going to be what? -6. So y4 -4. Everybody okay? And now I can do basically, so now what I've got is my vector y, if you will, is vector 3, 4 minus 5 minus 1. And now all I have to do is solve ux equals y to finish this value. So now I have one more augmented matrix. I have to solve u ux equals y. So in the augmented matrix here, my u is 4, 1, 4, 2. Zero minus 3, 2, 4. 0, 0, 1, 0, and 0, 0, 0 minus 2. And so I'm going to back substitute again and go as quickly as I can. This last equation is minus 2x 4 equals -1. So I get x4 from half. The second to the last equation, I love it, is x3 equals -5. Bang, got that. So now I got 2 out of the 4. The next equation gives me minus 3x2 plus 2x3 plus 4x4 equal to 4. Well, I know these numbers are. So this is going to be minus 3x2. That's going to be -10 plus 2, -8. So x2 is equal to -4. And finally, the last equation is 4x1 plus x2 plus 4x3 plus 2x4 is equal to 3. And now I know the first or the last 3 x's. This is going to be, what was X2, -4. 4x3 is going to be -20. And 2x2, that's going to be +1, is equal to -1. Right. 3. That's going to be -23 plus 3, so x1 is 13. And so the total solution to the original system is 13.5. I'm very close. Those, this is -23 on this side, right?
Yeah.
Swing that over here. 26. I'll divide by 2. What's that?
Why would it be 20?
I don't think so. I'm putting myself, you see, that's gonna be -23. So that's gonna be +23. And 3 is 26. There, and there, dude. Everybody okay? with it? So it's 13.5 -4, -5, and 1. And that's a solution to the different system. Now, some of you might complain a little bit, maybe rightfully so, that, oh, yeah, but you had to do 2 systems, and that's true. However, a computer can do this very efficiently. And oftentimes, especially if the original matrix is sparse, how many of you have heard of sparse matrix? Did you ever heard of that? This is something that you encounter in a lot of computational stuff. It comes up a lot in computer science. So what it means that the matrix has lots of zeros in it. Maybe it's a very large matrix, 100 by 100, but there's a large number of zeros in it. This happens quite a bit. LU factorization is very, 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 very fast to do this, because when you have sparse matrices, it's, you know, even though the matrix itself may have a lot of zeros, and its inverse might be not sparse at all. It might be full of all kinds of complicated stuff. And so, in that particular instance, LU is extremely efficient. So I'm going to do a couple of examples. So this is how you would use an LU factorization if you chose to do so to actually solve the system equations. You know, he did this sort of thing just in lockstep. The big question that you might have at this juncture, well, okay, where'd you get the LU factorization equation? I'm going to show you how to do this. But first, I'm going to talk about special case. Let's suppose that A can be reduced to echelon form by adding multiples of rows to a row below. Okay, so suppose that yes.
Is that two racks below? Like.
Oh,
it can only be three,
Anything
like-
below, I get your question. It could be any row below,
Okay.
right? So here's what I'm taking off the table for right now. I'm not allowing you to do row swaps, right? And I also want you to sort of, for it to echelon down, that is, take a multiple of a row and do a row above it. Now, you might protest and say, well, you can't always do that. And that's correct. You can't always do that. And so this will, after I go through how to do this one, it will require a slight variant in the LU factorization. And notice this also sort of takes off the table multiplying A by a scalar, right? Other than, remember how another row operation multiplying any row by a non-zero number. And we're not really talking about that, but it doesn't matter. And the reason is we only want A in an echelon form. We don't need it to be row reduced, so we don't really need that part of it. So let me go through and kind of pick it apart. I've got two examples kind of worked out. Let me tell you why this should work in the first place. Remember how all the row operations were multiplied by matrices? Remember that bit from last time? You always multiply. So what does it look like? What is someone on the example? What does this matrix do to another 3 by 3 matrix? Well, what it does is it leaves first row alone, second row alone. And then it takes -3 times the first row and adds it to the bottom, right? So this is one of these acceptable things where I add a multiple of, in this case, the first row and add it to a row below it, the third row. Everybody agree with that? And this is the reason why I'm doing this. This is actually, notice it's a lower triangular matrix. If I allowed to add something to a row above it, it would be an upper triangle. Here's a lower triangle. Notice all these row operations matrices, these elementary matrices are all invertible because we can all undo them. And so if we take A and do these row operations in tandem, we reduce it to its echelon form. All of these correspond to these kind of matrices that just do this. They take a multiple row and add it to a row below it. Notice that this is also a lower triangular matrix. When you multiply the lower triangular matrix, you get a lower triangular matrix. And A is actually equal to K 2, 1 inverse. So here's your lower triangular convertible matrix. Notice it will always have ones on the diagonal because every one of these has ones on the diagonal. And that's kind of your magic matrix. So how do you figure out what this is? How do you actually work it? Let me do an example. Let's go back to this matrix. This is a first example that I had for y'all today. And 12, 0, 16. Okay. So here's the way that I do this. This is my A. And while I build my A, so what I'm going to do is I am going to work this to echelon form. And I'm going to keep track of what I'm doing there, and I'm going to use that to build L. So I'm going to build L as I go along. And this is my first pivot column here. So so I want to use my first column of this for L, but I've already got a problem. Anybody tell me that this can't possibly be the first column of L? By the way, what size should L be? It should be 4 by 4, and so should the U. Well, what's wrong with this? I mean, I've only got one column here started, and there should already be a complaint. Yeah. Right. We need ones down the diagonal, right? Well, I can solve that problem. I'm going to replace this column with a 4th of it. 1 minus 1, 2. And this is going to be my first column. Now, remember, I'm working A to echelon form. So I'm going to use this first column as a pivot. I'm going to take out everything under it, right? Because I'm working to an upper triangular form. 0 minus 3 to 4. Multiply by -2 and add. 0, -2 and add. Add. Swimmingly. And I'm thinking 3 and add. 3. Everybody get it so far. What's the pivot entry? The second column. Yeah, I mean, it could be, it can't be that, right? Because that's already in the row first thing. It could be this or this, right? We're trying to work from top down. So here's the pivot entry. I want my second column of L to mimic this, right? This should be a 0 there, and this should be 1, 0. Everybody see where I got that? Right? It's the same principle here. This is going to be the column here, and I key on the pivot entry. I want 1/3 of that, and that's my entry here. This, of course, all this garbage up here has to be zeros, right? And I need to have 1s here. Everybody okay so far? Now I'll repeat the process in the sense that I'm going to reduce this again. Yes.
So we only take what's below the pivot?
Yes, that's what we're doing. Yeah, and so I will expect now in the next step to have a two column. Sorry. So here's what I'm going to do now. I'm going to use this to take this out. Same top row. 0 minus 3 to 4. I'm already cool here. And -1 times this plus this. 0 minus 1 times this. 2 minus 1 minus 2. Like all that. Yes.
How do you know when something's an L?
What's that?
How do you know when to do something to L? If you just keep adding numbers to L?
Right. So now I'm at this stage. Now look in this column. Right. What's the pivot entry here? Well, you could choose it to be this one or this one, but we're going from the top down. So I'm going to key on this. Notice I've already got a 1 here. Right. So 1, 2. Right. So what I've done is I go along. It's the first thing I did is I scaled that first pivot column. And that's where I got 1 minus 1, 2, 3. Then I got here, and I know in the second step, I only need 3 of the numbers out of the column because 0's got to belong to the top. So I scaled that down by -1/3, and I get 1, 0, 1. Next. Then I work my way over. I've already got a 1 here, so it's 1, 2, right? And in the final step here, I'll do that here. 4, 1, 4, 2, 0 minus 3, 2, 4, 0, 0, 1, 0. And of course, I can use this to just take out this 0, 0, 0 minus 2. And that last one, of course, has to be, I know for a fact the last column is 1, right? And so this is actually my U. And that should match up we had before when I first did the example, and it does. Let's do another. I think trying to clear it up. I hope it'll get. But before I do another one, any questions on the procedure there? Yes, ma'am.
Okay, so why didn't you just go ahead and use the third column with the one before and L? Why did you have to change that to 1, 2?
The third column with the,
Yeah, right there, because you already have the 1, right? So why did we have to change that to 1 and 2 for L?
because what happened is I've got the 3 here, so it's not an echelon form.
Okay,
So I gotta take that sucker out first.
okay, that makes
Right.
sense.
Is that okay? Okay, this is. I'm gonna do a 3 by 5, so we do something that's not, square. Yeah, so let's do this. One, 5, 1, 0, 4. 2 minus 2, 3, 10, 12. And 4 minus 4, 15, 40, 30. Now, let me point out this matrix is 3 by 5, right? So if I do an LU, here's what I'm looking for. You gotta have a match there. That's gotta be a 3 by 3. And the other one's gotta be the same size as A because it's an echelon form thing. So this is what I'm looking for. I should be building my U. I'm working toward my echelon form U is 3 by 5. And the L I build along the way should be 3 by 3. So let's see what happens. Let's kind of repeat this out here. So let's start here. And I'll build like I did before, I'm gonna build U in parallel. Or I'm sorry, L in parallel. 3, 12, 4, 15, 14, 38. In parallel. I'm gonna build L. So my L is gonna look like, my L's gonna look like this. It's gotta be 3 by 3. So it's gonna be 1, 0, 0, 1, 0, 1. So look, I already know all the 3 entries in, right, for sure. So my first pivot column is this, correct? And lucky me, it's already got a 1 on top, right? So in one step, I already know 8/9 of what this matrix looks like, right? So there's my first column. Now, do an echelon form, and we're now in search of where the next pivot falls. Multiplies by -2 and add. It's -2 and add. It's -2 and add. -2 and add. -2 and add. That. And multiply this by -4 and add. -4 and add. Add, so it's gonna be what, 32. And this is gonna be 22. Okay, where's the next pivot? It's the 3 in the third column, is good. And so What goes here? 5, very good, right, because I gotta scale this back down, right, and so that's gonna be 1, 5. Therefore, the second column lines. And so I've got this finished out. What I don't have finished is I don't have the U yet. So I've got to continue to get into echelon form. U 1 minus 1, 0 to 4, 0, 0, 3, 6, 4. And to finish this off, I'm going to multiply this by -5 and add. Times -5 and add is going to be 2, and with -5 and add. And good, we're all out of pivots, and this should be the LU form. If you multiply this lower triangular invertible matrix to this other one. Okay, any questions, guys, understand the procedure on this? Okay, so the next thing, the obvious question is, Jim, you always had these things that worked out the way you said they could. You could always reduce from the top down. You can't always do this. However, let me give you a simple example. Yeah, good luck getting that into lower left or lower triangle without doing rows, right? You're kind of hosed on this, right? So that might be distressing because, oh my goodness, what an easy example of where you can't do this process that I've done here. But it's not really an issue because what you can do is instead of doing LU, where this is strictly a lower triangular matrix, you can do what is called, you can generalize this to, and we're not going to talk about this too much, we're going to generalize this to a commuted lower triangle. This allows you to commute rows, right? And so what do I mean by commuted lower triangle? Well, let me give you a lower triangular. You might have something that looks like this. This is what you want it to look like, right? You may not be able to get an L, you may not be able to get a lower triangle, but you might be able to get something, or you can get something that looks like this. If you had to switch some rows around to make things work, and 12, I'll let down 3. Now, this doesn't look lower triangular anymore, and the main reason is because it ain't, right? It's not. Right? However, in principle, there's no more difficulty solving this, right? Because all you have to do is go pivot from left to right. This equation is easy, right? Solving that, and once you solve that, this equation is easy. Once you solve that, this equation is easy. And once you solve that, this equation is easy. All the way down the line. Everybody okay with that? So even though you can't always do LU, you can always do a permuted L like this if you like. But I just want you to understand the procedure. The easy case, is everybody kind of okay with that? All right, any questions? We will continue our adventure next time, and I will get the room and we'll talk more about the research. Y'all have a good one. We'll see you on. Yes.
For the L, the 3x5, it's 3x0.
Oh, because you got to have something that's worth on you, right? Because my original A is 3x5. That's changed if I made up. And your new convention on 4 is 3x5. Because if this one is like 2 row up here, right? So now fill in the blank. Your L pattern is 3x5.
I'll like